Hello everyone, my name is Abbas Milani. I'm presenting this today from the University of British Columbia in Canada. First of all, I would like to take the opportunity to thank ICMSN to give me the opportunity to present this keynote, and also my apologies that I couldn't be there in person to also interact more with my colleagues and peers. So the title of my presentation will be on digital twinning of advanced manufacturing in the Industry 5.0 era, with a focus on a thermoforming study. So a little bit about myself. My lab here at UBC is named Composite and Optimization Lab. I serve as a Tier 1 Principal Researcher in Sustainable and Smart Manufacturing. So really, my main area of expertise is on textile fiber reinforced composites, and more recently, their biocomposite alternatives. That includes their fabrication, testing, modeling, simulation, and also integration of the AI and digital twinning technologies, as well as the Silk Road economy when we talk about the sustainable composites. I also serve as the Director of Materials Manufacturing Research Institute here at UBC, and my lab is part of the Composite Research Network in Canada. And I would like also to acknowledge that I'm presenting this work from the traditional unceded territory of Silix Okanagan people here in Canada. So a little bit about the institute. Really, those of you who have visited Canada and British Columbia, you know UBC has two campuses, one in Vancouver, one in the Okanagan. We are located in the Okanagan campus. They are about 4 hours drive apart from each other. But really, the institute serves as a multidisciplinary bi-campus research hub to bring the basic and applied science researchers together. And by doing that, really, we try to have around 50% of our members from engineering, but another 50% from outside. And we create the clusters and program that may be traditionally a bit underrepresented, or there is a dislink between the researcher. That's really the mandate of the goal, to catalyze this high impact cluster of research across the university while we're working with other universities and organizations. So you can see some of the different pillars that we have. On the top is more on the applied side, from aerospace, biomedical, building, and so on. But as we move forward, it becomes more on the core science. And we work closely with government and industry partners on each of these clusters. So these are examples of some of our present clusters. By all means, if any of our participants in the conference are interested to work with UBC MMRI Institute within this cluster, please reach out to me. So we have clusters on the biocomposites, on human comfort, on the plastic recycling, circular economy in general, AI applications in manufacturing. But today's keynote will really focus on this emerging aspect: create immersive technologies within the material science and manufacturing practice. So why this is important? I believe digital twins now having really critical role in integrating basic and responsive research. I don't want to call it applied. I would like better to call it responsive research, because we may do applied research still in the academia, but may not be necessarily responsive to industry needs. So when we say responsive research, meaning that's the true applied research that right away meets the need of industry. So in this spectrum of starting, say, from developing or discovering a material, a resin at the chemistry lab, all the way to use it in the actual car manufacturing floor shop, uh, this normally translation takes about 10 years on average, from the discovery to application. But if we want to do a systematic research, really that this stage is more generic, to bring the labs together from different disciplines. And of course, that is a long-term investment, long-term collaboration, basically establishment. But often it lacks the clarity on what's the objective, what's the final, basically, application, because no one knows yet. On the other end, when there are projects defined by industry directly. They are narrowed in their scope. Normally it's risk-free and bureaucracy involved, but this can be normally one lab takes over and then other labs basically support them. So if you think about this spectrum, this can really become a push and pull. As the industry defines the project, we know what's the next generation of the basic research 5 years from now on. But vice versa, when we have some vision about a new material and about technology that is not in practice, this can really be flourished by close leadership and advisory role of the industry partners. How we fill this gap or shorten this translation from basic to applied research, or let's call it responsive research, I believe that's where the digital twins, including immersive technologies, play huge role in this era. Because imagine when you're going to a virtual world, basically you can, but researchers and industry, imagine how that application will look like at this time of the basic research, even though that application doesn't exist. And vice versa, you can use it back way to basically reversely engineer your basic research, right? So I think that's where the digital twin and including immersive technology, I feel that it plays a huge role as we progress into fifth industrial revolution, which I will describe a bit further in a few slides. So today, again, I'll really focus on extended reality and AI-based operator training, excuse me, and process optimization in thermoforming. So basically to see how we can combine immersive technologies with emerging AI technologies to help thermoforming processes for industry. This project is led at our institute by one of my former PhD students and now a PDF, Dr. Iman Jalivan, and has partners, industry partner Kohler, who you may know that is one of the major manufacturers of the bathtub across the world, and is funded also by New Frontiers in Research Fund in Canada. So just as a reminder, for some of you may not know the formal definition of immersive technologies, there are different really definitions out there. But at the end of the day, when we say immersive technology, we talk about digital tools, systems that create or simulate a surrounding environment, engaging one or more of the user senses that can be visual, audio, and so on, to produce a feeling of presence or immersion in that environment. So that environment can be fully virtual, meaning you're really disconnected from the physical real world. It could be on the other side fully reality, which then is not immersive. But between, we have the augmented reality, where the majority of what the scene you see is the real world. But there is some overlay of a digital tools that expands the reality and gives you additional information. And then there is this new version, which is augmented virtuality. So it means the majority is virtual, but there is some sense or some objects from the real world also merged there. And of course, the combination of this is the mixed reality, where actually physical and virtual worlds start interacting with each other, which is the topic of actually today for me to discuss that, how that can come to the manufacturing process and link the material science to it. So with that definition, I want to a little bit now position this strategically. So what is the vision around the world in the industry, really how to make use of these digital technologies, is we are in the era of Industry 5.0 or the fifth industrial revolution. So historically, industrial revolution started in 70, 80 when the mechanization started. Humans started using the mechanical system, the steam power, and so on. And then further on, electricity came. And then automation came. That's where the computer came in, robots came in, mass production started, digitalization started when AI kicked in back to 2011. This was the concept from Germany. That we move towards smart factories or cyber physical systems, right? But today, as we speak now, we are in the fifth industrial revolution, which now human comes back to the center of this revolution. So personalization and humanization becomes critical, which was missing in the fourth industrial revolution. Now, a little closer to see the difference between this recent revolution change from fourth to fifth. So really in the fourth, the focus was about the smart factories, automation, AI, IoT, big data, and as we speak, it still is there. So it's all about production driven, mass production, efficiency of energy, you want basically in a way to remove the human, minimal effect of human there, maybe just to monitor the automation. So you can see that in that vision, the factories of future would look like really no workers, which is not good for humanities. But now, soon we noticed that that was a wrong revolution. We switched as of 2020 to Industry 5.0, where the human-machine collaboration, here you see at the right image, becomes critical, meaning it's still the human role is central, but assisted by this digital technologies. So then the customization, personalization is very critical, and this environment or Silk Road economy comes in, and so on. So currently we are in this era, and when we talk about human-machine collaboration, I'm sure you can think this immersive technology is one of the best means or interface to facilitate this collaboration. So looking at the bibliographic trend, you can see around the same time that 2020 really did extended reality picked up. That's where the Industry 5.0 kicked up. And that's still really is highlighted research in the literature. The gap is that how, again, from the basic science, when we develop this technology in the computer science, in AI industry, how do we connect it to the real world where the operators, engineers are there, and how these physics and AI should come together under this interface for that human, basically machine or human computer interaction and collaboration, let's call it. That's the better word. So I think there are a lot of talks and vision about it, but I think this is one of the first projects actually testing such thing at the lab scale at our institute. And today I will present some preliminary results where we are at that. So thermoforming setup, I'm sure many of you already know about it. That's where has been a primary manufacturing technique for forming thermoplastics or thermoplastic composites, if fibers are involved, into complex 3D shaped parts. So that be that the bathtub, that's the Kohler company, one of our partners that I mentioned, be that in the automotive, be that in the boat industry, aerospace, and so on. So really you have your thermoplastic sheet or composite, you heat it, preheat it, so that it becomes soft enough to form it. So as you form it, it could be vacuum, just form it. It comes to the mold shape, and then at the right timing, you have to let it cool and demold it and basically take out the part, and then it's ready, the 3D. Of course, easier said than done, but there will be problems because during this manufacturing, of course, the heat is not uniform. In the beginning, you have the controlled heaters, but as you form it, some parts of the sheet comes to the contact with the mold sooner than the others. So neither the heat is basically because the conduction, convection, and those changes the mechanism is uniform, and nor will be the thickness of the part uniform because of that. So there will be some defects. But at the end of the day, it's a very rapid production technique suitable for complex geometry and quite cost effective, though it has its own complexities to deal with, right? It's a very large market, currently at 47 billion. It's going to reach estimated at 74 billion globally by 2034. So at the bottom, you can see some examples of those defects that in some companies can be as high as 30% the rate of the failure after thermoforming. So yes, it's automated fast enough, but at the same time, there are risks of the failure, and it's high, up to 30% sometimes. So you see the final formed part, it can have cracks, tear, which are completely useless. It may be some shearing, webs, and so on. Sometimes it's repairable on site. That causes overhead time and cost for the companies. Sometimes they have to just redo and just throw this material away. So how to deal with that? This is where we think XR, extended reality, can come in at the first step to train the operators. Because if you want to train the operators for those trials and errors, these are physical system, expensive, takes time, you're wasting energy, material. Why not to do that training in an immersive environment? And optimize in a way the process as well, and then come do the real manufacturing. And even so, for that process optimization, As you do the actual manufacturing, this becomes every failure in new data. So it can be used by AI to assist the operator what to do better next time. That's where that AI human collaboration comes in very closely. So those of you working in polymers know very well that when it comes to thermoplastic, you have a narrow window of the forming. So you have to just hit the material enough to be in kind of above the glass transition, but then as soon as you form it, it cools before it comes below the glass transition and becomes too rigid and fragile. You have to finish your forming. So you have a narrow window there to really play around, and that's where all these problems comes, because it depends on the geometry, it depends on the material, depends on this initial heat, and so on your vacuum, performance, effectiveness, and speed, and so on. So that's where we think machine learning can help, because at the end of the day, the agent, which is in this case can be the operator along with that AI agent, at each state, meaning at each manufacturing that they do, they take an action. It could be just setting up the heater differently, and they see something happens. For example, there is a shear, tear, and so on. But there can be also a future reward meaning zero defect, how close we are to the best. So by measuring these things and feeding back to the AI, and then while the operator kind of interfere with the digital tool through XR, be that for training, be that for the actual process optimization, all this can come together to push that automation while human still is at the center of this. So back to that industry 5.0, that gives that vision that is still the human role is central, but is backed by AI tools. Now, how do we do this? First of all, we develop some simulation, finite difference-based simulation, so that there is a physics base. It's not black box AI. No, it is, let's call it gray box AI. The second thing, we created a prototype setup of industrial thermoforming in our lab, and we designed the parts and so on. We developed the XR extended reality in Unity, and then we also performed some user experience dashboards and so on, so that the user can have better understanding of how this XR works, for be that the self-training and so on. But then for this, we really use both virtual reality, meaning the entire manufacturing is done in virtually, or mixed reality, meaning there is the actual setup, but things are virtual, objects are interacting back and forth through user. So we also perform user study for both methods, and we compare the effectiveness of these two technologies with the traditional video training, which is very common in the lab, in the manufacturing. A new technician comes, someone just trains them through watching a video and maybe a manual or a few trials, right? So again, for those of you who are not familiar, in virtual reality setups, you have to have these handheld controllers to go around and like a gaming, right? But in mixed reality, it's hand-free, which is really good for manufacturing, but then you have to use your hand gestures to prompt, basically to perform some prompts as you do. So a little bit will take time for the user mentally to memorize this, but once you get hold of it, it's very straightforward. So I invite you as participant to know which of these methods you think is better. So what we really did during the user study, we recruited about 26 participants, and each participant took about 45 minutes to do the basically test, with some introduction on what is the study about, demographic information collection, and then experimental procedures, and filling out the questionnaire at the end, and some interviews as well to get their general oral feedback. So for the test, we really use the Latin square sequence, meaning that we have 3 means of training: virtual reality, mixed reality, and the video training, basically. But we grouped these participants into 3 clusters, and in each cluster we just randomly follow the different order, not randomly, sorry, in the Latin square sequence, so that at the end we have also an understanding if the order of this trial matters or not. So what we measured, usefulness and ease of the use of this training means training effectiveness, the trust, satisfaction, reliability, and overall performance. So these are more subjective for each user, but also we measured as an objective quantity how long it took for them to do a particular terraforming task. And here you can see a distribution of our demographic data, female and male, the same participants. Because we did it in the academia, the majority were our master's and PhD students who participated. But we had some participants from the high school, our technicians, and so on. And about 50% they knew about digital technologies from the past, and some they didn't know and needed some introduction, extra introduction to be par. So here you can see some actual scenes of these two setups. So this is the virtual reality. As I mentioned before, everything is virtual, including manufacturing. That physics simulation is linked, integrated here. So as the operator changes, for example, these knobs, those heaters get different temperatures, and so the sheet underneath will have a different temperature as well. So how this will work is based on the physics that it communicates over cloud back and forth with this XR device. The same thing in mixed reality. The difference is, as I mentioned, there is no handheld controller. Now you use your hand gesture, and now there is actual setup, and then these virtual setups are overlaid on this, and the same thing. You can change the knobs and the temperature virtually. This sheet here virtually will heat up, and then it will be formed, and so on. So I can definitely later, if you're interested, send you a link to watch the video demo of this. It's quite entertaining, actually, to see how students liked it and worked with it, and especially those who hadn't worked at all with the thermoforming in the past, including non-engineers. So anyway, some of our results that here it showed it along each of those output metrics. There is quite a bit of distribution you can see among different participants and different training modes, but no significant statistically difference was found based on the participants' prior exposure. So interestingly, those who didn't know about XR, actually they did the same way after that initial introduction as those that knew about XR. Completion time analysis revealed that the virtual reality, when it's completely virtual, is the fastest, I think not surprisingly, followed by the mixed reality, and actually video training takes longer to watch, to learn, and then do it, right? So that's the gain that you can see it practically matters, right? And these are the stacked total scores. At the end, mixed reality got 2.3, followed by virtual reality, which is very similar to the video training. So the mixed reality, where you mix really physical reality, actual setup, where still you have a sense of what is happening and you can use your natural human senses. With the virtual/AI reality, you see it, then you have quite a meaningful improvement. And that was very, very nice to see as a proof of concept within this case study. So a little bit more detail. I don't want to go through all the statistical analysis, but you can see under mixed reality, under each of these performances, these green values, it was the highest when compared to the other, from basically 0 to 1. But interestingly, under the trust, actually most participants trusted the video training. And that makes sense because these are extended reality, virtual or mixed reality. These are emerging technologies, and many say, oh, how should I trust it? That what it shows me is real. So the trust was really opposite. And actually under virtual reality, as I mentioned, it was faster compared to the other ones. So bottom line is that if you really want more formally decide which technology is better, you have to do a multi-criteria decision making, because there are some conflicts among the ranks or scores of the alternative versus criteria. We did that based on different weightings, but at the end of the day, no matter what's the importance of those criteria weighting, the virtual reality always ranked really overall first. Sorry, mixed reality. So where we are now we're really trying to take the same interface on the mixed reality, add two aspects to it. One, add the large language models coaching. such as ChatGPT. So actually, the operator can ask questions from AI, not in a structured way, in a non-structured way, back and forth. So to help them during the process optimization or training. Number two, how about the cognitive analytics? We know that when you use this virtual reality or mixed reality, there are advantages, enhancement in terms of your sensory improvement, your physical performance, your cognitive performance, empathy even, but there are some disadvantages. It may cause you confusion, dizziness, and so on. So how can we measure that aspect to make sure we are not adding a psychological or physiological burden on the user while we're trying to help, we just unhelp something else. So to do that, we're really working with professors from psychology, computer science, cognitive science in a very collaborative way to understand how really we should measure this cognitive loads and embed it as a dashboard so that the user himself or herself can see it and a supervisor, and then decide when and if such technologies even should be used. Don't forget, Industry 5.0 at the center is about human, not AI and production driven. No, it's value driven. It should have a value for the user. If not, then it has to be modified, these technologies, or customized. So that's where we are now. And when I say about cognitive load, again, there are really different layers of it. So it can be intrinsic, meaning the complexity of all this new information, digital comes on top of the actual manufacturing, physical manufacturing. It can be extraneous, meaning it can distract your memory. You may forget the main things that was needed in the actual manufacturing control. And it could be German, meaning that there is your brain is deep processing of this all new information, digital AI, plus the physical, what you see in the mixed reality. So how this will all come together in the cognitive function, still don't know. That's where our current research is. So with that, I thank you again and the opportunity, and I wish you all the best for the rest of the conference. Thank you.